Hi everyone, so this tutorial here is based on the pre-Leaving Cert examination 2019, I suppose more commonly known as the mock paper for the DCG higher level. Okay, so I'm just going to do in this tutorial the section A, the short questions, so I'm just going to get stuck right into them here. First one up here, question A1. You'll see some of these guys here have already done, but you'll see further on in the tutorial how they're actually completed. Okay, so focusing here on question A1, the graphic below shows a number of plant pots. Okay, so you see a number of pots here in the little graphic. The drawing on the right shows the plan and elevation of one of the plant pots. So the first thing we're asked to do here is to determine the true length of the line of intersection between the internal surfaces A and B. So the true length of that. So I'm just going to shade in the two surfaces we're talking about here, A and B. And the line, of course, of intersection between those is the line at an angle here, you see in the corner, this line here. Alright, so again, we're asked to discover the true length of that. And as we know, with the true length of a line or true shape of a surface, we need to look at 90 degrees to it. So what I'm going to do here, I'm going to project an auxiliary view of this line. So we'll project out at 90 degrees to it, and we'll plot that in our auxiliary view. Okay, so here's my x1, y1 of that auxiliary view. Alright, I have the top and bottom point of that line projected out here. Okay, so in order for me to determine the exact position or angle of that line to get the true length of it, I need to take my measurements here from our elevation of the same line, just in the elevation view, and I'm going to mark off those points at the corresponding height. From my XY line in elevation, measure the height of the top and bottom of the line of intersection, and simple as that, join those 2 points. That's giving me the true length of the line of intersection. Okay, so you have the top point of it here and the bottom of the line there, which gives you again the true length of the line of intersection between both the shaded surfaces. So quite simple there once you create your auxiliary view, if you can get your head around that. As we know, you have to be looking at 90 degrees to it in order to get the true length. So moving on to part B, determine the dihedral angle between the surfaces A and B. So we need to get our dihedral angle between those surfaces. Okay, so what we're going to have to do in this case, we're going to have to look along this line now that we've located here to get a point view of the line of intersection, and this in turn will give us our dihedral angle between the surfaces A and B. So the first thing what I want to do there is project another and set up another auxiliary view along that line. Project that out. And draw what I call now my x2, y2 line. Okay, so I'm going to call this point here on the corner point X just for convenience. Alright, so what I want to do is locate that point in our auxiliary 2 view. Okay, so with your auxiliary views, to take your true height, you come back 2 views. So back 1, 2, and I'm going to measure this distance from x1, y1 back to that point. And I'm going to set that off here from x2, y2 to locate what I'm calling there as point X. Okay, so this is now looking along point view of this line here, as you see it. Okay, so we need other heights from the surfaces A and B. What I'm going to do here, I'm going to project up this line along here, back to my first auxiliary view, if you like, to take in point A. I'm going to move it over here, point B and point A, which is the top of both of those surfaces. I'm going to project those up into my first auxiliary view. Okay, I'm going to project the height of them, which is basically the height of the top of my flower pot in our original elevation. Project that up there. And from there, I'm going to project that into my second auxiliary elevation, just to get at the position of those 2 points. Okay. And simply what I do in this case, I now measure back my distance again, so I'm going back 1, 2 views from that x1, y1 line. I'm measuring my distance back to point A here and back to point B, and I'm plotting them now along that line of projection. There you have it, the distance from x1, y1 back to point A, measure out on our second auxiliary. The distance from the x1, y1 back to point B, measure out on our second auxiliary. When I join those 3 points, that then should give me my dihedral angle between the surfaces A and B. So I'll just indicate that there. That angle between those 2 lines is my dihedral angle. Question A2 here on this paper. You can see this one here is the axonometric axis question. And just to start off, you see your axonometric, your 3 axes here, X, Y and Z. You have your front elevation and side elevation of the chimney breast, as is shown here on the image. So the graphic below shows a living room in a modern house. A 2-sided fireplace is in the central room as shown. The drawing on the right shows an incomplete trimetric projection of a similar 2-sided fireplace using the axonometric axis, as I mentioned here. Okay, so part A here, you're asked to complete the axonometric projection of the fireplace. So what I'm going to do here, I'm just going to transfer the points, first of all, of the fireplace in between the X, Y and Z axis. So we have my true elevation here, if you like, with your true sizes, and you have your side view here. So what you do here in this case is you project those points of the fireplace back parallel to the axis here, Z in this case. I'm going to bring these points back first of all. Right, from the front elevation, and the same base point going to bring parallel here to my x-axis and project it back from the front corner here of the fireplace. Now generally when I'm doing these questions I like to set out the ground of the actual fireplace first. That way it just gives you a better picture of where it's actually standing in the corner, if you like, of the three axes. So just to highlight that a slight bit here, I'll go a bit darker on the two outside surfaces. Back to here. So it kind of shows you where the opening is here on the middle. So basically what I do from here on in, I project all of my points here on each corner parallel to my z-axis in, and the corresponding points here then that relate to the same point in both views, you project them across here parallel to your x-axis, and where they meet, that basically gives you the points and will lead to your 3D graphic of the chimney breast, which will complete part A. So for the corners of the actual opening for the fire, I'm going to bring these two back here now, and again where your hidden detail is here, we'll project across, and that will represent those two corners on the front of our fireplace. There you go, you now have your 3D model, if you like, of the fireplace here. So basically each of the corners here is probably an idea if you want to label each corner as long as they both correspond in each view. So that way you'll be able to track which lines or which points are projected back from both the elevation and side view, and you'll be able to plot them then nice and easy. If you're confident enough, you may not need to do that, but it would help if you're in any doubt. And I'll just shade that in a slight bit just to show off the surface itself. Not necessary to shade it in the question, but it just does make it stand out that bit more. Okay, so moving on to part B. Now that we have the fireplace in place, sorry, just cover that bit in there as well. Determine the true shape of the rectangle sloping top surface, of the structure. So this rectangle sloping top surface here, we want to see the true shape. And we don't see the true shape of it here in this view because we're simply not looking at 90 degrees to it. So there is one or two ways we could do this here to determine the true shape. Okay, so keep in mind it just says the sloping top surface, it doesn't say on the left or on the right. So what we can do here, I know I have my true length of the surface here. Okay, so simply what I can do, if I project out at 90 degrees to this line, okay, I now know the length of that surface there. Okay, so they're projected out 90 degrees. So you can imagine if you're folding out that surface from that line, and that will give you the length of it. Okay, and now I'm looking in at 90 degrees to it. In order to get the true depth of it then from the front to the back of the chimney breast, well, we have that here in our end view. So you can just come with your compass. We know it's the true length here from front to back because that's our end view. Measure that with your compass or set square and simply stroke off from there on each line and join those back. And that now gives you the true shape of the required slanted surface. Okay, we'll just shade that in here in pink. Okay, just to clarify, that could also be done another way here, where you could extend up these two ends on your end view and get your true length here from your front elevation there and mark that similar to the last way method of doing it. Mark that up here from the top of the side view, and that will also give you the true shape of the surface. Moving on to part A3 of this short section A short questions. This one here, a little bit of geometry involved. So the graphic below shows the solar panel which is on the roof of a residential building. So you can see the solar panel here, an image of that, and this graphic represents the plan view of it. The drawing on the right shows the plan and the sloping rectangle of the sloping rectangle surface ABCD, so ABCD, and the elevation of the line AB, so the elevation of the line AB, which is projected up from the plan. You're asked here, so the surface ABCD, you're told, is inclined at 50 degrees to the horizontal plane. Okay, so this surface ABCD is inclined at 50 degrees to the horizontal plane. So what we do know about that is that the line AB here in the elevation, we can see that that's horizontal. Okay, so this line is horizontal. So we need to figure out the height, I suppose, of CD up here for the elevation. And the way we're going to do that, we're going to imagine we're looking in along a point view of the line AB here in order to get the true inclination of 50 degrees. So what that requires is for us to project an auxiliary elevation. I'm going to project up here the line AB. I'm going to also project up the line CD because we know that's the width of it as we look down on top. I'm going to come up here, mark off my X1, Y1 perpendicular to that, and just label that X1, Y1. And I'm simply, if you see here, I'll just line up point B, you would see that's projected straight up, then point A projected straight up. Just while I've it set up here, I'm going to project up point C and D as well. Okay, we don't yet know the heights of those. So what we do know here is that point A and B is a height off the ground here from the XY line. I'm just going to measure that with my compass. So I'm just going to mark that from my X1, Y1 line. That, if you can imagine, you're looking at a point view here, so you can see point A and B behind it. Alright, we're told that the surface ABCD is inclined at 50 degrees to the horizontal plane, so 50 degrees to this. I'm just going to draw a horizontal line from AB just so I can measure off with the protractor. Okay, an angle of 50 degrees, which is here. And once I draw that line, we know now where it crosses our line CD coming up here. That represents the edge view of that panel. Okay, and simply what I've got to do now is measure our height from our X1, Y1 leg up to CD, or the point CD. And that there will give us our heights for point C and D in our elevation. As I come along now, I projected up those lines earlier. I'm just going to measure our distance from the X1, Y1 up to point C and D, and I'm going to mark them off in the elevation. Now we have point C, here I have point D. I can join those up in order to complete the rectangle. There you can see our solar panel drawn in elevation. And the fact that you have these dividing lines, if you like, here to create these little rectangles, I would project those up to get your full marks onto the corresponding lines in elevation. So these points here, project them up onto the line CB, and likewise with all other points around the perimeter of the panel. That's your entire question A3 complete. So first we projected our auxiliary view looking up along the line AB. We came in at an angle of 50 degrees, then once we located point AB, so this angle here, 50 degrees as given in the question, and that helped us determine the heights then of CD, which we then projected into our front elevation. So the last part of this short questions, I'm going to do all four, is question A4. The graphic below shows a necklace pendant. The pendant is in the form of an octahedron and consists of 8 equilateral triangles. So each of these little triangles is an equilateral triangle. The drawing on the right shows a plan of a similar octahedron which is orientated as shown. So part A of this question, find the altitude of the octahedron and project its elevation. Okay, so first things first here, I know the position of it in plan. You can see here as it's drawn. So I'm going to project up first of all the points that I have here. Okay, so our 3 lines there projected up. So the first thing, next thing I'm going to do is, we know it's built up of equilateral triangles. Alright, so the width of it, again, looking down from the plan view, we know the end of this little triangle, I'll call this point O, call that maybe X and Y. So for this triangle here, so essentially what I want to do is to fold up that triangle, so I'm looking down at 90 degrees to it. So if I extend out both ends of that, I know the true length of the equilateral triangle, because I see it here in plan, is this length here from X to Y. Okay, so that distance there. So I know if I swing that from point O till it crosses those lines, that's going to give me the true shape of the equilateral triangle that we're dealing with. So if you can imagine there, that's the true shape of the equilateral triangle that the octahedron consists of. And now I'm going to project that up, point O at the base of our octahedron here. If I project the new point X and Y, so we'll go X1 and Y1, if I project those up onto the XY line, you know, that's the true length, that's the distance there from point O. I'm going to rotate that up until it hits this line back to its initial position, if you like, and that's going to give me the center point as regards the height. Okay, I projected that up. Again, imagine I'm swinging that up to the top again. That's going to give me starting points for my octahedron. You can see the base triangle here as we're looking in from the front. This is going to be our base triangle, and I simply go up the same distance from point O at the base to what we'll call point O at the top of it as well. We'll say O as well. So because we're looking in from the front here, this is the view you're going to see your 2 triangles, this guy here and the one at the bottom. So again, essentially I just folded up or hinged up from our point O here, rotated up that triangle so we get a 90-degree view of it, which gives us its true shape. Projected that up to the XY line, and again I rotated the length of it from O out up until we meet our initial position of that. So part B, draw an elevation of the octahedron when one of its equilateral triangles triangular surface is in a horizontal position. So I'm just going to come out here to the left. I'm going to draw my equilateral triangle in a horizontal position. So I'll just get the true length of the side of that again. Make a point here. Take that distance as well. So I've basically drawn that triangle as if it's sitting flat on the ground there in that horizontal position. Right, so if I call it X, Y and O, I'm going to project those points up to the XY line. We have X and O. So we know as I'm looking at the elevation of that, this is my line. I will see looking in at the edge view, if you like, of that triangle from the ground. So what I do know now is that I can show a true length of one edge of that triangle. So if I swing from X here an arc, I know my length XO here will represent another side of my triangle. So where those two meet, this line here is true length line. So if you can picture that triangle, XYO is lying flat on the ground here, and the next one then underneath it is falling out towards us till we see this point. Okay, so I come across horizontal from that. Measure out the same distance as the side here. So this, if you can picture again, is falling away from us. Join it back to that point, like so. Slightly tricky to visualize with this octahedron. This blue surface here represents our triangle on the ground. This guy, if you like, is sloping towards us, as with this guy is kind of sloping away from us as well at an angle. So basically that's your elevation of the octahedron drawn. So the last thing you're asked to do is to project its plan, and that's the question complete. So I'm just going to project these points down to the plan to complete that question, and I hope that helps you for revising and to learn the best way and methods to complete these questions.